just
All right.
That's okay.
Good to go.
We just do the voice.
All right, welcome everyone. Thanks for coming to the lunchtime talk today. Last night we were very lucky to have Mike Cheadle do a presentation on spreading centers, and that was co-authored by his wife, Barbara John, and fellow professor. So today they're switching roles, and today Barbara is going to do the talk, co-authored by her husband, Mike. And briefly, Mike is an associate professor of geophysics at the University of Wyoming, and Barbara is a professor of structural geology / tectonics and igneous processes at the University of Wyoming. And Barbara, who's going to be speaking today, has a long list of publications, many PhDs and master's students, and her primary research interest is to understand the processes of lithospheric deformation both on the continents and in the oceans. And the aim of her approach is to use well-placed field studies as natural examples of structural and petrologic processes. Her previous and ongoing research can be divided into 3 general areas, including deformation of the continental lithosphere, deformation of oceanic lithosphere, and magnetism and deformation. So, please help me welcome Barbara.
Thanks very much, Cynthia. So a number of you, I think, were here last evening and heard Mike's talk. I'll have a couple of slides that are duplicates. The majority, hopefully, will be new and interesting. My talk will probably not be as comprehensive. It's going to focus basically on looking at hydrothermal vent fields. Now, I know most of you are really aware of sort of the hydrothermal system in Yellowstone, and so this is basically an analog system at the seafloor. And we're going to learn, hopefully we'll learn, about sort of 3 different types of hydrothermal systems, what we consider high temperature ones, intermediate temperature ones, and low temperature ones. And something more about sort of the fluid chemistry, the kind of character of the vent system themselves, and a tiny bit about the fauna, but to be perfectly honest, I'm not a biologist, so I'm not the best person to be discussing that. But I'll show you some pictures, okay? So let's go. We're going to explore the deep, and we're going to talk about discovering seafloor hydrothermal vents. We'll start with the first sort of recognition of hydrothermal vents, and then go on to talk about some that Mike and I have been involved in recognizing. So hydrothermal vents, as I said, they're basically seafloor geysers or hot springs, similar to what we have in Yellowstone, okay, under Yellowstone Lake. They release hot, mineral-rich water at the seafloor, okay, and I'll show you a little model of how that kind of works. And prior to their discovery, we inferred that life basically on Earth depends on sunlight or photosynthesis. But with the recognition of these hydrothermal vents in the deep sea, we actually realized that vent organisms can survive and thrive under high pressures, high temperatures, in toxic sort of mineral plumes, or what we consider to be toxic mineral plumes, okay? Yet these organisms are happy as clams, literally, okay? Without sunlight. And they're able to convert these mineral-rich fluids into energy, okay? And so this is what we call chemosynthesis, and there are chemosynthetic bacteria, obviously in Yellowstone, and there's also these chemosynthetic sort of organisms that we see at the bottom of the sea. Okay, and so basically sunlight is no longer a required sort of attribute for life. And so basically hydrothermal vents and the recognition of hydrothermal vents has actually helped us redefine the requirements for life on Earth. Okay, so marine hydrothermal vents. This is a map showing basically in red all the recognized marine hydrothermal vents that we know of today, and this is today. And every day that we go out and look, we actually find more. So what do you see? You see them basically preserved or actively venting these fluids along the mid-ocean ridge system that Mike talked about last evening. Okay? And the initial discovery in 1977 was on the Galapagos, or near the Galapagos, at this star here. Okay? So again, you see that there's not a lot of hydrothermal vents that are recognized down in the sort of southern latitudes below the roaring 40s, and that's basically because we haven't been there. That doesn't mean they don't exist there. It's just that we haven't looked. And similarly, we're just starting, as the ice starts to melt due to some foreign circumstances up here in the Arctic, we're starting to recognize vent systems up there as well. So we have them basically distributed throughout the global mid-ocean ridge system. So just a little bit of history. The Galapagos hydrothermal expedition in February of 1977. It left from Scripps Institute of Oceanography. It went on the Lulu, which is this very strange ship that has a hole in the middle of it. It's a catamaran, basically, with a hole in the middle of the deck that launched, or was able to launch, the manned submersible, or the human occupied submersible, for the gender non-specific, Alvin. Okay? So Alvin is launched through a hole in the middle of the deck, in the aft part of the deck. And the other instrument that was used was called Angus, which is an acoustically navigated geophysical underwater system. Very clever. So Angus actually was put down initially at the seafloor. And Angus has sensors on it that could actually look for EH anomalies, sort of particle anomalies, temperature anomalies, and so forth. And so these are sort of the tools that the Galapagos hydrothermal expedition used, both Alvin and the camera sled. And in essence, the evidence for the hydrothermal vents came from initially the recorded temperature anomalies along cracks that were visible on the seafloor. So there's a camera on Angus, as well as these different sorts of sensors. And again, this was 1977. The Navy had developed a variety of things, but the sort of the academic research community was fairly limited with this. So Angus looks pretty primitive, right? It's just this skeleton with a bunch of stuff hanging on it, and then it's tethered to the ship. Okay, so there were these recorded temperature anomaly along fissures, so it seemed like there was hotter water coming out of cracks on the seafloor. And then Angus actually got these sort of images, and they were literally pictures on film, not digital things. So we're, I think, probably all of an age to know what film looked like, whereas my students have never, ever seen film. And they recognized, especially this guy, Jack Corliss of Oregon State, he actually recognized these dense accumulation of white clams. So these are photographs printed of the clams, and these little white things are those clams, okay? And they sampled the clams and they brought them up to the surface, and they're not small, right? I mean, you'd think, oh yeah, those things are maybe like an inch across. No, they're huge. All right? And so there were these clams that were living near these temperature anomalies, and they said, okay, maybe we should go down in Alvin and check it out. And so they did. And as they moved along the fissures, they actually came across the vent fauna, including these spectacular tube worms, okay? Or what are called Raftia pachyptilia. There's probably a biologist here who can help me. Anyway, so these are these spectacular tube worms that were originally first recognized associated with the hydrothermal vent systems at the Galapagos in 1977. Okay, so some quick facts. That was sort of a brief history of time in terms of hydrothermal vents, but let's think about, in general. So the vents themselves are recognized as common, relatively common. You saw their distribution. We find them in every ocean. I'm not saying they're all hot, but we are finding these vent systems in all oceans. So throughout, any spreading ridge, any spreading rate, as Mike was discussing yesterday. The deepest is actually the BB vent. It's in the Cayman Trough, and Mike briefly discussed that last evening around the mid-Cayman region. And it's at 5,000 meters water depth, so greater than 16,000 feet below sea level. You actually have hot 470-degree water emitting from sort of the ridge axis. Black smoker fluids are the hottest that we have in terms of the vents, and they're about between 350 and 400 degrees C, except at extreme depths where the pressure allows water to boil at higher temperatures, okay? So this is about 760 degrees F, much hotter than you're gonna broil things in your oven, for reference. And in fact, those temperatures are hot enough to actually melt many solid metals, okay? And the vent fluids themselves, as I said, are typically superheated due to the increased pressure of the overlying water. And I'll show you in a second, they form as a result of the ingress of cold seawater into fractures of the basaltic or any host rock crust and sort of leaching heat and then buoyantly rising back out. Okay, they leach heat and minerals. Okay, so this is just a really simple schematic of a mid-ocean ridge vent structure. And I tried to sort of give you, oops, it got cut off here. But anyway, I give you an idea of sort of a model. And this is for hot sort of black smoker fluids. So here's the ocean crust, the spreading ridge here in essence. And they're very commonly associated with the spreading ridge because that's where at shallower depths, you actually have the melt, as Mike described. Okay? And so you have the cold seawater, bottom temperature of the sea below about 1,000 meters is 2 degrees C. It's pretty constant. It's not freezing. It's just about 2 degrees C. And this cold seawater here, then will penetrate into cracks in the seafloor. And so that cold water will ingress into the basalt or any other host rock type through cracks. It will heat up as it goes down towards this sort of magma or the hot sort of lower crust. And then it will start to buoyantly rise and it will go through what we call a reaction zone. That is a region where it interacts with the host rock. Now for black smokers, or most often black smokers, that's basalt. And you guys are familiar with basalt in Hawaii, in the Snake River Plain, not so much in Yellowstone, but Hawaii, Snake River Plain, Galapagos. It interacts with that, or in slow spreading environments, it can interact with gabbros or even peridotite. We have mantle exposed at the seafloor locally in slow spreading environments that Mike showed you, okay? And that reaction zone sort of dictates the kinds of elements that are basically scavenged by the fluids that are emitted out of the vent, okay? And so the water will react and then move up buoyantly because it's now warm and hit the cold seawater again and then it will form a plume and it will start to precipitate out different kinds of minerals, okay? And so you can have helium, you get iron, manganese, methane, CO2, hydrogen sulfide in these plumes, and then you get lots of different types of minerals as well as different gases, okay? And I'll pass around a sample in a few minutes showing you some of those minerals, but we'll go over them. Okay, so that's, a very simplistic sort of model for mid-ocean ridge hydrothermal vents. Okay, now we have, as I mentioned at the outset, 3 different types of hydrothermal vents. These high temperature, and again, depending on the depth at which they form, high temperature that is greater than about 320 degrees C, low pH black smokers. That is, they're emitting this sort of particle-rich lead, sulfur, iron-rich material back into the sea floor, okay, and you form these chimneys that look like black smokers. And so I'm going to show you a couple that I've been involved in discovering at 1320 degrees on the mid-Atlantic ridge, and also the black smokers at Pito Deep that Mike was discussing yesterday, okay? These smokers can be up to 180 feet high. They're very sort of relatively delicate, narrow chimneys that just protrude out of the seafloor, and you'll see some of them. Then we have sort of moderate temperature, what we call Van Dam type. That's named after Karen Van Dam, who was a vent geochemist who died at a young age of breast cancer, actually. And so we have named them after her. And they're at 120 to about 220 degrees C, and they're neutral pH, okay? And then finally, we have these low temperature. So far, we've only really found one of these, Lost City type, and they're carbonate chimneys, and they're associated with high pHs, okay? And I just wanted to remind you, pHs, not everyone, probably everyone in this audience does remember, but sort of low pH, 1 and 2 are sort of battery acid, stomach acid, lemon, things like that. Neutral pH is sort of milk and human blood. And then as we go into more alkaline or basic, high pHs, we get to, bleach and ammonia. So just keep that in mind as we go through these sorts of details of the different types of vent systems, okay? So low pH, battery acid, high pH, very alkaline. So if you get high pH on your hands, the oils from your hands start to turn into soap, okay? All right. Okay, so Mike discussed the mid-ocean ridge system and this sort of plate boundary that extends for about 55 kilometers, around the world, kind of like a baseball seam, it just completely encircles the globe. And again, it's about 8 times from Denver to London. That's the length of this ridge system, or 1.5 times the circumference of the Earth. So it's a fairly important and fundamental sort of feature on the Earth's surface. And again, these plate boundaries, these sort of plate spreading boundaries, are where we find the majority of the hydrothermal vents. Okay, and again, as Mike showed you, and very briefly, we have the tools to explore the seafloor. So first you go on a ship, and this is a variety of different ships, including the drill ship, the mothership, now for Alvin. So it's no longer a catamaran with a hole in the middle. You use this A-frame and you launch it out the back. Probably a little more stable. And then this Pourquoi, which is a French ship. Actually, the French, it's interesting. It's actually, the French Navy uses it half the time, and it's a civilian ship half the time. So it's a very interesting and confusing sometimes sort of thing. So colleagues of mine were scheduled to be working on the Mid-Atlantic Ridge when the Air France plane went down a number of years ago, and they were immediately taken off the ship. The French Navy got on the ship, and they went to go look for the Air France plane. So it's just the way different governments deal with, large, expensive sort of scientific vehicles. And then we talked about the human-occupied or manned submersibles. And so here's the Shinkai, and here's Alvin. And again, these are 2 of the vehicles that we've used. And then we talked about the remotely operated vehicles, which are really probably the vehicle of choice mostly these days. The human-occupied vehicle, you can really only stay down for 8 to 10 hours. And then, oxygen, you have to get the oxygen scrubbers out to try and, make it tolerable for human occupation. And then you might have to pee and, stuff like that. So, we most commonly use what we call ROVs, or the remotely operated or tethered vehicles. And these are just different examples of types of tethered vehicles that we use. This is Victor, and these are full-size humans, and you can see that it's a very large instrument. In contrast to little Hercules, which is a NOAA vessel, and the same guys for scale, okay? So, and these types are used offshore for oil and gas, off of rigs for repairs, really, really commonly. And that's what they were developed for, okay, was for the oil and gas industry. So we use these sort of vehicles. They characteristically, but not always, have it's difficult to see here, but they have like a little basket in front to put samples in. They have all kinds of devices for measuring temperature, salinity, particle content. They can photograph, and they can also do near bottom bathymetry, so we can get at the topography of the seafloor. And as Mike showed you, we commonly work in a shipping container that's been craned onto the ship and strapped down. It's not very spectacular, although on the French one, it was designed by the Tour de France sort of people that monitor the actual race, and so it was really cushy compared to the US sort of shipping containers. So we could actually fit quite a few people in here. And here we are looking at a variety of monitors, and in fact, this one was when we were looking at a newly discovered hydrothermal vent on the mid-Atlantic ridge. Okay, and then another tool that we're starting to use more and more are these autonomous underwater vehicles. And as Mike said, they have no cables. This is just launching it into the sea, and then you let it go. You program it to actually fly, literally, at a very close range to the suspected seafloor. Occasionally it crashes, and its nose is a little dented there. But it flies close to the seafloor and gets very high resolution sort of bathymetry, which we use in order to then pick things like, say, where hydrothermal vents are. And I'll show you some examples of that. And then Abyss is a German torpedo-shaped sort of autonomous vehicle. So each country has different sort of styles of how they're going to design them. Their engineers design them differently. But Abyss is also an incredibly useful tool. And so here are the different types of data that you can actually acquire from these autonomous vehicles. You can get bathymetry, you can get temperature, you can get sort of particle concentrations in the seawater, and you can actually get photographs of the seafloor, which again are very useful. Okay, so let's talk then about these high temperature black smoker type vent systems, and I'll take you on a little tour in the Pacific and the Atlantic to look at newly recognized ones that we've come across. So the first will be Pito Deep, just here. And so Mike discussed sort of these 4 to 6 kilometer sort of high scarps that we were able to actually look at the construction of the ocean crust in. So how do we build this 60% of the Earth's surface in different environments? And I'm going to take you on a little tour down here to this sort of orange bump. Okay? And this is, in essence, the propagation of the East Pacific rise into existing crust. And this is sort of Pito Seamont. And slowly. So here, whoops. Okay, not going so good, but anyway. Here is the seamount. And with Century, the autonomous vehicle, we did a tiny little area of the top of the seamount in order to get really high resolution bathymetry, in order to think about, okay, what, if there are hydrothermal vents there, where are they? And can we locate them? Because if you just drop a remotely operated vehicle off the back of the ship and just drive around, it's like looking for a needle in a haystack, okay? And so we did this high resolution bathymetry in an effort to try and understand if there is. So here is our bathymetry. This is 1 meter resolution. So in essence, you could see this table right here on the bottom of the sea, okay? And this is the actual spreading ridge, and you can see, in essence, off-axis. This is 2.5 kilometers. So off-axis here, all these sort of highs, these lumpy, bumpy sort of highs. Here's an old sort of volcanic construct that's being ripped in part, in half, by the ridge, okay? And so if you slowly look at this at an oblique angle, you start to recognize, so this is the exact same bathymetry. These are the sort of red lumps and bumps. And then look at all these little pointy spires here. There's dozens of them, okay? And the majority of these pointy spires are actually active hydrothermal vents that we recognize, okay? And so having this high resolution bathymetry gave us the opportunity to pick a place to focus and go to look at this potential vent field. And so this is just, and again, we had 1 day of ROV time at the very end of a cruise and then 10 days sailing back to Chile. So we had to do the best we could in a short amount of time to make the captain happy and all the ROV pilots and everybody happy. But what we found in our very short reconnaissance was at least 7 active vents, more than 50 chimneys, some up to 22 meters high, so about 70 feet high, okay? And the active black smokers that we were able to sample had temperatures of greater than 370 degrees C, okay? And so this is one of our black smokers here, and it's just pumping out, you know, this black smoke, these particles of sulfide, iron sulfide with trace amounts of gold and silver, cadmium, and so forth, okay? And this is the chimney itself, and then it's got a lot of fauna on it. And so we were able to actually take our ROV and photograph it all the way around, all the way up. And so we can give you a link to a website, and if you're interested, you can download a 3-dimensional photo mosaic of the chimney. If you want your own, you know, hydrothermal vent at home, you can have it, okay? So this is just one of our hydrothermal vents. And then these are, in general, the different sort of images that we had of these different black smokers. And so this is the Jason team, that is the team in charge of the pilots and the navigators in charge of the remotely operated vehicle. They said, oh, well, there's no vents named after like the tools that we use. And so this is the Jason vent, named after Jason, the instrument that we used to actually discover it. We have Medea, which is in essence a little buoyancy thing that holds the fiber optic cable mid-water so that you don't get too much tension on it. Sentry, this was named by Mike because he thought this looked like a human holding a gun. You get to have some fun when you're out there. And then here, the pilots, in order to actually sample the fluids and figure out the temperature and even the composition of the fluids, the pilots have a tendency to go up to a really actively pumping sort of part of the vent and then take the titanium claws and break it off and then stick a thermal probe directly in that venting fluid, that rapidly venting fluid, in order to get the highest temperature. If you just kind of cruise up here and go in the top, it's going to be really diluted by seawater, okay, cold 2 degrees C seawater. So if you break it off part of the way down, then you can get a better representation of the actual temperature that the water is coming out at, okay? And so here's the claw holding a sample, and right there, John, if you want to start passing it around, that's the piece that we broke off, so that's a 1.5-year old piece of hydrothermal vent from Pito Deep. And if you look at it, it's sort of, if you look sort of through the orifice, you'll see it's zoned. And so there's chalcopyrite and there's pyrite both. So these are copper, iron, sulfide minerals. Maybe after it gets light again, we'll look at it. Anyway, so that's that piece specifically just being passed around. It does have a lot of sulfur, so your hands are going to stink afterwards, sorry. Okay, so Mike, if you can, sorry. So this is just a little compilation of the Pito Seamont vents, and I think you guys, we had a meeting with you from the ship just before we found the Pito Seamont, so this is a chance to see.
Is this the actual color?
Yeah. This is the actual color. So this is not looking like an artificially colored version of Mars or something. We have a variety of crabs and shrimp, gastropods. And this is the temperature probe. Yeah, he was just putting the temperature probe in after he'd broken it off. So here are a lot of little crabs. They love cadmium and antimony and, you know. what we consider toxic, they don't. And I was telling somebody at lunch that in the last sort of 10 years, the lighting that we have on these vehicles has improved dramatically. And so that's why you have such beautiful videography, because you can actually see things in contrast to sort of low lumen sort of stuff. Okay, so again, another quick view. Let's go to another high temperature black smoker system. Now we're not in fast spreading crust, but we're going to go to the mid-Atlantic ridge. And this is the Irinovskoe. It's actually, the Russians said that there were going to be vents there. They hadn't gotten there, but they said there should be. So they're named for the Russians that were looking for the vents there, okay? So I went again with the French. The Germans graciously provided their ROV because there's starting to be sort of almost, well, it wouldn't be called a gold rush, but a mining rush on the mid-ocean ridges looking for minerals. And so the Russians and the Germans and a number of countries in Europe are actually staking claims on mid-ocean ridges outside the EEZs, okay? I'll show you in a minute. So anyway, so the Russians staked their claim, but they never saw the vents. So we went and saw the vents. The Germans are very interested in terms of natural resources, and so they were happy to provide their autonomous vehicle on a French ship, even though they don't always get on, just to go see how well it worked. Okay, so we were, and so this is one of these detachment systems on a slow spreading mid-ocean ridge that Mike showed you. This is at 13 degrees north latitude. And these are the dives that we did with our remotely operated vehicle, and the area here for the vents are right in this area. And so they're in fairly deep water, 27 to 28 meter water depth. There were hydrothermal vents, a lot of active ones and inactive sulfide spires. They had, you know, fluid temperatures between 320 and 364 degrees and low pH water. Okay? So again, these black smokers are characteristically sort of acid pHs, and when we get to the Lost City type, they're going to be very basic. And in fact, we found over 1,000 square meters of massive sulfide outcrop throughout this area and this area. Now, to me, that's not very significant in terms of trying to find a big ore deposit. But if you find a lot of these in a small area, then it starts to potentially, well, not in my mind, but in some people's mind, to be economic, okay? And the minerals include pyrite, chalcopyrite, bornite, chalcocite, and atacamite. So these are all copper-rich minerals. And so here's one of the vents, and again, we used the high-resolution bathymetry in order to find them, and there's the vent. And this guy's only like 2.5 meters high. It's just a little squirt. But it's emitting relatively high temperature fluids at low pH. And again, as I was mentioning, these black smokers are sort of a modern analog for ancient mineral deposits. In fact, we have some of these deposits in the state of Wyoming where there's actually collision belts in the state, okay? And so here again are all these black smoker sites throughout the modern day mid-ocean ridges. Here are the black smoker sites outside of EEZs, and these are where governments are starting to stake claims. Now, to me, this seems like a long way from anywhere, and how can that be economic? But as we start to use more and more copper and precious minerals, well.
And is there no movement for a treaty for the deep ocean? Like
yes, it's starting to get to one. And in the last couple of years, people are starting to get pretty upset about, you know, the potential impact of mining and how that's going to impact filter feeders and the whole biosystem. But it's just starting, okay?
Hey, question.
Yeah?
On that back, that you had that map there.
Yeah?
When you were talking about the Pito one, where is that geographically?
Pito is out here.
Well, way off in South
Yeah.
America.
Right, yeah. So it's outside anybody's EEZ, so anybody can go there and harvest it. So again, I said that these are sort of analogs for what we call volcanic massive sulfide deposits. These are things that we find on land today. And so this is, in essence, a sketch or a schematic of sort of the vent system in 3 dimensions and the mineralogy that you might anticipate. So anhydrite, pyrite, and quartz. And then as you go down, you get silicified pyrite stockwork, chloratized sort of ugly basalt. It's had a lot of fluid go through it. And in essence, but these things aren't very deep. And then you have sort of this surrounding sediment pile, okay, that will have a lot of iron, potentially manganese, possibly copper, coming out of the plume and just being deposited on the sea surface. So the mining idea is to, since you don't have to dig up a huge, it's not like an underground mine along a quartz vein or something. It's, in essence, a surface feature. So you can just sort of scrape that off is the idea, okay? And so again, these high temperature mineral resources are associated with the black smokers. And their chimneys and their surrounding deposits are going to have copper, iron, zinc, lead, silver, gold, and byproducts of cadmium, tin, and antimony. So these are all things that we use. And so that's why a lot of different governments are interested in them. And these are just some of the samples that we collected with the French on the mid-Atlantic ridge. And you can see just beautiful pyrite and chalcopyrite here, pyrite, and then I don't even know what this purple, it's not amethyst, this purple mineral here. And this is, yeah, so these are just, images. Okay, so Nautilus Minerals is a group out of Australia, and they're actually actively pursuing this notion of harvesting or mining, deep sea mining, okay? And so this is volcanic massive sulfide mining and production. And again, they have deposits offshore Papua New Guinea and Tonga, and they're looking for high-grade copper, gold, zinc, and silver. And so this is a schematic from their webpage, just showing you have a support vessel. It's basically flat, and you just load it with stuff. You have, in essence, a seafloor mining tool, one of these sort of either this cabled one or this one, where it sort of cuts it up and then basically vacuums it up to the sea surface and deposits it in the ship, okay? Don't ask me, this is just what they're doing. And they actually they've developed these tools. These are actually real live versions with humans. These are not just, artificially produced images of these different types of seafloor mining tools. And they're starting to think about going off of PNG, collecting copper, gold, silver, zinc, and so forth. So
are they only doing the seafloor? They're not doing the vents in particular?
No, they're taking the vents off and everything. They're just going along and just scraping it up. It's like snow plowing, yeah, kind of with a vacuum cleaner above the snow to hover it up to the top. Okay. Okay, so quickly, let's look at the moderate temperature, sort of what we call the Van Damme type vent systems. And again, Mike went over this. It's this tiny little 100-kilometer long spreading ridge in the Caribbean Sea. It's the mid-Cayman rise. And Mount Dent, as Mike described, the Van Damme vent field is at relatively shallow water, between 700 and 800 meters water depth. We found about 60 mounds there and chimneys, seeps. They're low temperature. Okay, they're about 220 degrees C, and they have methane. They produced EH anomalies, and all the metallic particles are reduced rather than oxidized. Okay, and the active vents where they exist have pyrite, chalcopyrite, and anhydrite. And the fauna themselves are diverse. There are tube worms there, so this is in the Atlantic. Some have suggested that there are only tube worms in the Pacific, but we found scarce tube worms in this particular environment, okay? Now, if they came through the Panama Canal, maybe, I don't know. So it's not that they're species that are only able to exist in one place or another. Somehow there has to be communication. This is the, that's the reduced versus oxidized state of, yeah. It's just what, so an EH, if it's a positive or negative, means it's oxidized or reduced, okay? And so the fauna, tube worms, shrimp, squat lobsters, and a variety of fish, okay? And so here's Mount Dent, and as Mike showed you, there are these fractures that are starting to cut through this. The ridge is actually, you know, originally over here, and now it's starting to migrate in this direction. So there's heat that's actually probably coming from magma at depth in this area with the fracture here. And so, again, the high resolution bathymetry, here's the top. That's this sort of spire right here with the ROV, and you can see the cable sort of buoyantly lying around. And it's built on quite a little sort of dump of stuff, okay? Pre-existing sulfide. And so the mound itself, this is that image, and you look at it and it's white. It's like, is there snow on this? You know, what is that white stuff? And when you zoom in, well, here it is, it's white. And you zoom in more, and it's just millions and millions and millions of little shrimp, okay? So it's completely white. And so this is, again, just a video that we were involved in with NOAA, so the National Oceanographic and Atmospheric. And yeah, so this is the ROV going down through the sharks in the nice warm water in the Caribbean.
Roger, thank you.
What's interesting to note here, if you look through the shrimp, you can actually see when you can see the rocks behind, they're actually a dark bluish grey colour. You see yellow colours or everywhere else, that's almost certainly iron oxidizing, whereas gone basically.
Yeah. So this is our colleague, Chris German, at the Woods Hole Oceanographic Institute speaking. There were just, again, 2 chief scientists on the boat, just like Mike was talking about.
Those biologists that are interested, look very carefully at the dorsal organ and look at the quite distinctive shape compared to Rimicaris exoculata that's found in the North Atlantic. They're distinctly different.
And so here you have the water being, this is the hottest water right here. And that's only 120 degrees C. Well, relative to 400, yeah. And here's more of the chimney. Now to me, why do they have eyes? Yeah. They have eyes.
Yes, Chris.
And here are these.
Gulf of Mexico, there's lamellibrachia and sepiophilia. This looks, in a way, more like lamellibrachia, but the coiling of the tube is more like sepiophilia.
So here are these.
But look at that! Isn't that just absolutely wonderful?
Exquisite is the word of the day.
Exquisite it is.
Remember, I did tell you at the start of the day today, the magic word for today was tube worm.
So this is pretty pathetic compared to what we saw from the Galapagos, but they're still there.
What is that?
So he's referring to this little, what I call a dandelion. So it's some.
Whatever they see is apparently they were seen on the Galapagos cruise as well. They were referred to there as dandelions.
Oh, the dandelions. Weren't they stalk sulfophores?
Kind of, yeah. But it's got a stalk. So this particular ROV doesn't have arms, so you can't collect anything, but it's got very nice cameras. You can't have everything, you know. Noah's got the cameras, but no arms.
So the swarms of shrimp, what were they eating?
Bacteria, yeah.
The bacteria are feeding on the hot water and the minerals.
Right, yeah. It's quite an ecosystem.
I hadn't heard about that.
Yeah, right.
So what ate the shrimp?
Fish. Okay. So this is just some of the imagery of these shrimp with their eyes right here, and their Rimicarius hibaceae. These are, we went and sampled them subsequently, and so this is them dead in a gloved hand, okay? In case, I mean, you don't know. I mean, we joked about, oh, let's have a shrimp barbecue, and then it's like with cadmium, you know, tungsten, tin, zinc, lead. Oh, that'll be great, yeah. Well, there's a thumb, so kind of that size, yeah. You maybe an inch to an inch and a half, yeah, okay? But millions of them. And then here, I mean, the photography on this is spectacular. And so here's one pregnant with the eggs, which is, you know, pretty spectacular. The temperature around this was up to between 120 and 200 degrees C. Well, we'd think so, yeah. But the pressure difference is what helps in terms of boiling. So we're getting increased pressure versus at Laramie, you know, you boil water at sort of 97 or something. Your coffee's cold before you start.
Is it possible that the eyes on the shrimp detect heat?
Well,
Detect any light?
that would be kind of what I would surmise, but I'm totally not a biologist, yeah.
Somebody doing research on their eyes?
Not that I'm aware of, but Mike, do you know? Is somebody doing research as to why these things have eyes? All the fish have eyes, everything has eyes. Are they just vestigial?
Yeah, that they could be, and do they actually see?
Do they, yeah, right.
They may be vestigial and left there. But
And
not
just
see.
like, yeah.
But there is a lot of fluorescence.
Phosphorescence, yeah, yeah.
Creatures down there, so something.
So it could be for predation, it could be, yeah.
But birds see different ranges of light than we do, just because it's dark for us, who knows what they're seeing.
Yeah, right. But it's pretty dark. Anyway, okay, let's do quickly the last sort of system of hydrothermal vents, and it's a system so far only recognized on the mid-Atlantic ridge here at 30 degrees north, and this is this Lost City type discovered in 2000. And the Lost City, it's wild. Here's the mid-Atlantic ridge right here. The plates are spreading asymmetrically, as Mike explained yesterday. So about 70% of the plate spreading is towards North America and about 30% towards Europe. And the vent field, you see, is not down here at the ridge, but is sitting at this high, this bathymetric high, hydrologic high as well, on this sort of cliff face overlooking the Atlantis transform. And it was totally serendipitous that these were found. We were trying to finish the geology of this cliff face using remotely operated vehicles, and we were just basically bringing the ROV up to the surface, to the top of this sort of flat detachment system. And then there were these things that look sort of like corals popping up. You know, you're looking, there was a downward facing camera, and you look at it and it says, wow, corals at 700 meters water depth. That's interesting. And so I asked the captain to, because in this case it was 2000, a long time ago, the captain actually has to change the ship, the orientation of the ship, in order to change the orientation of the ROV, because it didn't have propellers at that time. So the captain changed the orientation of the ship. We let out some cable in order to let the ROV down, and we saw these delicate spires of carbonate, okay? Calcite and aragonite. And so we had one Alvin dive left. So the next day, there were 2 scientists that went in Alvin and with the robotic arms collected bits of the vents, measured the temperatures and so forth, and the pH. And so that's really how we discovered the Lost City. It was completely by accident. Because, I mean, how would you expect to have a hydrothermal vent like 15 kilometers off axis, 1.5 million years off axis? What's driving that? Remember I said you have cold seawater, it goes through cracks, it hits magma, it heats up, it rises buoyantly, it scavenges the metals from the surrounding host rock, comes out to the cold seawater again and precipitates. Well, first off, as Mike showed you, there's no basalt up here. There's only peridotite and gabbro. Peridotite and gabbro, what minerals are in there? Olivine, plagioclase, pyroxene. Okay, so now what? How many of you have heard of serpentinization? Have any of you heard of serpentinization? Okay, so serpentinization is basically you take fresh olivine, iron, magnesium, silica, and oxygen. You basically crack that. I'm looking at your fleece. It's that color. It's beautiful. You crack that and get water through it, and you hydrate that olivine, okay? And with that hydration, you basically, it's an exothermic chemical reaction, and so as a result of that, you give off heat, you give off methane, and you form serpentine, plus magnetite also, just as a side light, okay? And so these chimneys are basically the result of, in part at least, serpentinization reactions. And the reason why we have them here is because, again, this is a detachment fault. It's pulled out from the mid-Atlantic ridge. And as Mike said, you know, it can't go up forever. So it has to flexurally rotate, okay, and form this sort of gentle surface. And as that surface, you know, in essence rotate, you crack the top of it. You have peridotite at the seafloor. You crack it. You introduce water to it, and you form these serpentinization, the exothermic serpentinization reactions. And so we've looked other places for these and have yet to find them, but this is the first example. And so the Lost City vent field, this was on the cover of the journal that we published this in. Again, they're at shallow water depths, and this was in 2000, so we only had black and white photography. This is a mosaic, so you can see where we put everything together. But it's the old days. Anyway, so they're in shallow water. They're actively venting these low temperature, up to 90 degrees C, very, very alkaline. So pH is between 9 and 11, okay? With methane, they're at least, partially related to exothermic serpentinization reactions associated with the slow spreading crust that brings the mantle to the seafloor. And we have calcite, aragonite, and brucite. So calcium carbonate, 2 versions, and then magnesium hydroxide, okay? Basically interaction with seawater of these fluids. And they support dense chemosynthetic microbial communities, so bacteria, and biofilms sort of on mineral surfaces. Virtually no macrofauna, 2 fish, after about 16 actual expeditions to this area. So virtually no fish, but maybe that's the alkalinity. And we recognize 30 chimneys. They're between, most of them are between 10 and 30 meters high, 160 meters high, and we like to say that that's the tallest building in Wyoming, just for reference. And so this is just to give you an idea. Here, the size of whales, orcas, and humpbacks. Here's the chimney, a 40-meter high one. Here's the dorms at the University of Wyoming, just for reference. Okay, and so with that, I'd like to thank you. So, questions? Yeah.
Can you deduce how far down the magma may be and the cycle time that gets the hot water up based upon the temperature?
People can model that. Yes, so you can deduce it. But whether that modeling, because you have to know the flow rate and then the sort of thermal structure, and you have to have, So there's a lot of assumptions in that. Yeah, a lot of assumptions. But yes, it can be modeled. And then people are trying to use short-lived radioisotopes to try and get at potentially those flow rates as well, and the temporal history, as you say. Yeah, but the answer is I don't know. Yeah.
There's salt in seawater. I haven't seen, where'd the Na go?
It will go into anhydrite, in the black smokers, and then it can basically be, it just increases the salinity, in essence, of the seawater surrounding it. Yeah. Yeah?
Did you say that some of the vent field structures or whatever, that there was some found in the old oceans of Wyoming?
Yes. Yeah.
Can you say that again then?
So, okay, so, I mean, in Wyoming, you know, as we sort of put this craton together in the Proterozoic, we had boundaries, sutures, where we you know, collided continents, and maybe even sort of had an ocean and you know, crushed it. And so there are places at South Pass, I believe, and I'm trying to think. There's somewhere actually near Laramie, but I'm not sure exactly where, where you know, these sutures exist, where we are accreting different bits of continent from another continent to this one and crushing an ocean between. And there are these volcanic massive sulfide, well, they're very small, but there are volcanic massive sulfide deposits.
And that's like a supercontinent then, not the oceans that were in Wyoming much later.
Yeah, no, that's the building of the craton and not the sort of Cretaceous, you know, inland sea sort of. No, we don't have anything young in terms of these deposits. By young, I mean, you know, 100 million years or less. Yeah.
Also, are the water current rates ranging from almost still to something higher? Are they different by the different types of vents, the three different types of vents?
My impression is that the cooler the temperature, the lower the flow rate. That's just based on my personal observations. But looking at the sort of throat of the vent flow rates, I don't know how many people have been able to measure those. I mean, I'm just thinking of the watching particles move a short distance and how quickly that is and how robust that flow is. And my impression is the hotter the temperature, the more rapid, but I could be wrong. Yeah. Yeah?
So the black smokers and the Van Dam vent,
Uh-huh.
are they a similar mechanism? Because clearly the slower,
The
Atlantic mid-ocean
right.
is a different mechanism.
Right, yeah.
Okay, so what's the difference? What
Well,
different
yeah, so,
temperatures and pH?
right. So one suggestion is that the Van Dam either is the beginning of a black smoker system or the dying of a black smoker system. And so you get this sort of shimmering water and what we might call a white smoker system, where you have more barite and chlorite and things like that coming out. And so that's a suggestion, but whether that's, we have only recognized some of these things the black smokers we recognized the longest. And then the Van Dam was only discovered about 10 years ago. And then similarly, the Lost Cities was discovered 18 years ago. But again, to get back out to these places, to get more information, to look at the fauna, you have to get money and you have to write grants and be successful. So yeah, I don't know that that's been looked at that carefully. Yeah.
So just a comment, there's another type of vent,
Yeah.
hydrothermal vent in the Gulf of Mexico.
Right,
They're
the
very common.
seeps, yeah.
Yeah, they're more like seeps, and they support a wide variety of plant and animal life.
Mhm.
Mostly they're feeding on hydrocarbons.
Methane,
They're seeping off.
yeah.
Methane and
Right, and as we were looking at the Van Dam sort of tube worms, the second gentleman was saying something like, well, we see this in the Gulf of Mexico and they're similar to these particular types.
And those tube worms are huge. I mean, they're like, you know, the size of your arm. Kind of.
Is that right?
Yeah, they can get really
Oh, these are not.
No.
These are like, yeah.
But, and then to the other point about regulation, it's strictly, we have to do detailed surveys of the seabed wherever we're going to drill or put any kind of infrastructure to make sure we avoid any living bioharm of any kind.
Yeah. So, and there's beginning to be a lot more discussion in the law of the sea, especially outside EEZs, in order to think about, okay, you may not be disturbing a bioherm at the seafloor, but you may be disturbing the filter feeders that are in the water column. And so this is something that's just starting to be addressed. Because, yes, it's been that you cannot disturb, the living species in the rocks on the seafloor, but what about all the guys above it? And what happens if you start pumping cadmium into this, the water column? Will they be happy or not? Maybe they will, but yeah, we have to be careful. So, yeah.
Did I understand correctly, the images you had of the high-resolution topography, you got that with the symmetry?
We got that with the autonomous vehicles, and that's called bathymetry, yeah. Bathymetry, yeah. Okay. Yeah. Okay.
I was wondering what would be the radiation source if it was a dosimeter.
No. Sorry.
All right.
And so, yeah. It's a sonar on the bottom of the vehicle.
Yes.
Yeah. Okay. Sorry. Yeah.
Do you have to do these particular times of the year because the weather would probably impact you?
Yes. So whether you're French or Chinese or Japanese or American or whoever, you apply to your national funding agency, or actually Google has a yacht and has a research vessel, so you can apply to Google too, for use of their research vessels. And then they have schedulers who try to say, okay, well, this has all been funded for the next 4 or 5 years out. What ocean are we going to go to next? And how are we going to juggle all this? And yeah, sure, you can't be in the roaring 40s. Well, you can't really be in the roaring 40s, period. But but you can't be, in the southern hemisphere in June very successfully below 30 or south of 30 degrees south and have much success in terms of launching your vehicles, or in the northern hemisphere. So yes, there are people that try to schedule it so that you can optimize your weather window. That doesn't necessarily always work. I mean, Mike and I were on a cruise with the Japanese where we were in the Indian Ocean and we had 5 typhoons and we basically did nothing but run away from the typhoons.
What about the South China Sea and or the Chinese in general and what they're doing?
So the Chinese have been developing a lot of research capability. They have new research vessels. I think they have 2 or 3 new research vessels. They have new autonomous vehicles that look very similar to Century. I won't go into how they got that information and why, but identical would be the way to describe it. And so they are definitely, becoming more and more of a strength in the oceans. The South China Sea, there was a large international program, the International Ocean Drilling Program, that just recently, as of 2 years ago, had 2 research expeditions in the South China Sea to try and understand the opening of the South China Sea, the sort of temporal evolution of that, and think about potential resources associated with that extensional sort of setting. And so they are definitely getting more involved. They're getting a lot more resources put towards the oceans, and the South China Sea is definitely in there.
With the mining interest down there, they must be very interested.
Right, and there's a lot of pirates in the South China Sea, so it's a lot of problem for, just doodling around. You don't do it lightly. Yeah.
You said 1977 was when you guys first found.
Not me.
Well,
Yeah.
Corliss.
Corliss. Yeah. Right.
Whatever. Why did they choose where they went for that? Was there something they gave them?
Well, they knew that the Galapagos was Bob might even know better than I do. Yeah.
It's a young volcanic island, so.
Right. So they were suspicious because it had poked up above the sea, that there might be aspects of it that were still under the sea, that were hot and potentially interacting with the seawater. I mean, Hawaii's another example. But Galapagos is a little more exotic.
How
Yeah.
much are
vents heating up seawater vis-a-vis global warming, seawater warming?
Well, you saw the distribution on the ridges, and those were really big dots for really tiny pinpricks. Probably not a lot yet. Now, if we start to find more and recognize, that they're much, much hotter, but, that is a drop in the bucket.
As it were.
Yes, yeah.
It's been part of the global system for 4 billion years.
Yeah,
Still an issue,
yes, yeah,
an aspect.
right.
We're here because of that aspect.
Yeah, in fact, some people would suggest that those last vent types, the Lost City vent types, could have something to do with the origin of life in terms of the early Earth and, getting water and then water having abiogenic sort of methane formed and so
Did they
forth.
produce water?
No, they don't produce water, but once the Earth had water and we had plate spreading and we had this sort of system where we potentially are, hydrating the mantle and then forming abiogenic methane and so forth, and serpentinization reactions, and maybe, somehow we went from there. We went from there to here. Okay. Anyone else? Yeah, it's hard.
No big deal.
Yeah, right.
Just one little step.
Yeah, I'm just a geologist. Yeah. Yeah.
What's the shallowest vent?
Of these types, not including the vents in the Gulf of Mexico, I think probably on the order of 700 meters water depth. But again, we haven't looked everywhere. Anyone else?
There are not any remnants sitting on the shelf anywhere that you know of.
You mean getting ready to be subducted? Well, those are deeper because, as you start to flex the plate, yeah. Not that I know of. And, it's really hard to sort of back calculate the water depth of these ancient ones that are now slammed together on the continent, so, yeah. But, it's really, I don't know, how many of you have ever been to Cyprus? Have any of you been to Cyprus? Yeah, okay. So, so the first copper mines on Earth were actually in Cyprus. And those are related to this is a volcanic massive sulfide, and it's related to mid-ocean ridge hydrothermal vent systems. And so that early copper is from that system. Yeah, a place called Troodos, the Troodos ophiolite in Cyprus. So if you ever go back, wander around and look at the rocks. Okay, well, thank you all very much. There you go.
Thanks, Bobby.
Yeah, this is kind of a whirlwind of stuff.
Good stuff.